Hello everyone, my name is Konstantin Vladimirov. I'm compiler team lead here in Moscow. Also, I'm teaching at Moscow Institute for Physics and Technology. And the course on C++ we are beginning has been taught by me for over 9 years and was previously recorded in Russian and published on YouTube on this channel, gaining some popularity. This time I will be delivering it in English to make it accessible to a non-Russian speaking audience, for example, from countries like China, India, South Africa, Iran, and others. This is not an introductory course. It assumes prior knowledge of the C++ programming language and serves to deepen and systemize understanding. It is also suitable for professional development of working C++ programmers who use the language in their daily tasks. And let me talk a little about this course. This course is taught over 2 semesters, and there is exam only for students at the end of each semester. And during the course, assignments can be completed. And for students, I always saying, please send me your assignments. For you who are watching me on YouTube, I might say, please leave solutions and comments. It will be great, and for channel also. And slides will appear here, and this link also, you will find this link under this video, and code examples will be available on the GitHub. And let's talk a bit about C++ programming language. What is C++ programming language, and what can we say about it in general? Please think about it for a moment. And there are a lot of things we can say about C++ programming language. First, it is statically compiled language. What does it mean? It means that we have basically two stages of our execution of our program execution, program translation, and program execution. And when program translation is done, all bets are off. We compiled program, linked it. I would say compile and link instead of translate, because compile and link is much more convenient for me. And what else? We can say that C++ is general purpose. What does it mean? A general purpose language means we do not know precisely what programs will be written in it. As Bjarne Stroustrup, the creator of C++, said, he has no idea what programmers do with C++. This indicates that the language is not tailored for specific problem domains, unlike, for example, GPGPU languages, where the scope of solvable problems is limited. C++ is also statically typed. This is a significant advantage. And the possibility of translating a program, and you can see this translation process here and execution process here, the very possibility of translating a program is determined by the language standard. And let's examine what this is. And I strongly hope you will download a copy of the standard, final draft of the standard, and use it throughout this course. So, the language standard. A programming language itself is an agreement between programmers and compiler developers, and compiler developers are also programmers, yes, documented in a standard. The current language standard is ISO IEC 14882, and it was ratified in 2023 by ISO Working Group 21. Detailed information available here, and final draft, I believe you can Google a link on PDF of final draft easily. And it is the language standard, not a specific implementation, that is the final and decisive argument on how a program is translated. And what is a language standard? How do you think? Please think a moment. And the language standard is a list of diagnosable rules. Rules can be syntactic, and syntactic rules can be checked by a grammar. And what is diagnosable rule? These are rules such that if violated, the compiler is required to issue a diagnostic message and the program will not be translated at all. The compiler is not a static analyzer. The compiler is not permitted to have false positive. Syntactic rules are simple ones. You violated the language grammar, you have syntax violation error message. And semantic errors are really tricky sometimes because in the ideal world, an implementation that satisfies the standard should either translate the program or issue a diagnostic. And after program is translated, it can be executed. But what can we say about this program? If this foo is defined somewhere, then it is okay. But if it is not, compiler, while looking only at this context, cannot decide if it can be translated or if some diagnostic is required. So some diagnostics might not be so easy. Probably it will be linker who will issue diagnostic here. Let's remember this for a future. And when we will talk about language standard, we will frequently include references to the standard. Section numbering in the language standard changes between versions, like overloading. In C++ 17, overloading was described in chapter 16, and in C++ 20, overloading was described in chapter 12. And therefore, we will use symbolic references like not 16.1, but over.load, because over.load is the same for C++ 17 and for C++ 20. And by default, in this lecture, the discussion will refer to the C++ 23 standard with some mentions of the upcoming C++ 26. And let's do like the first really easy problem. To remember what C++ is, we will do it in C and then on C++. And imagine you are on a job interview, and I myself is a participant of job interviews from both sides really often. And okay, this is a problem just to assess coding skills. And this is classic problem. You are asked to implement a function to find the most significant set bit in a number. You can see some tests. For example, if number is 1, then answer is 0 because 1 is 0-bit position. If this is 6, then we have bits on positions number 1 and 2. We have 0 on position 0, 1 on position 1, and 1 on position 2. So answer in 2. Please convince yourself that here answer is 3. And of course, obvious, if we have a bit shift to 31 positions, then answer is 31. Yes. Okay. And of course, this is 3. How will we write it? Take some time. Please pause this video now and write this solution on a sheet of paper or in Goldbolt, and please do it in C. And let's assess your C language coding skills. And probably you came up with something like this. A naive C implementation, probably using the loop, iterating over from the most significant bit to the least, because we are iterating here from 0 to max bit, but we are reversing iterations here. Bit num equals max bit minus I minus 1. And because it is C language program and we do not know what is this type, we used some macro. And in the C language, we are using either macros or void pointers really often. And this macro is any suitable integral type. And here we have some mask, and we are starting with most significant bits, and then we are looking for next bits. And you might also convince yourself that if input data is normally distributed, this is even more effective than binary search, because if input data is normally distributed, then in binary search you will have an average like 5 iterations for 32-bit data, and for this linear algorithm you will have an average like 2 iterations. So this algorithm is good, but we definitely can do better. And please pause the video now and think about how you would improve this code. Still using C. Still using C. How will you improve? 3, 2, 1. Okay. Possibly you think, why do we need a loop at all? No compiler can optimize this loop, by the way. But we do have language built-ins and a compiler built-ins. Okay, let's use it for just unsigned. Not for every type now, just for unsigned. We can do a lot more better. A lot of modern processors have specialized instructions like count leading zeros instruction in x86, and using compiler intrinsics allows replacing the loop with a few instructions, which is much more efficient. However, we have a problem because we cannot do both. We cannot easily select the implementation based on the data type in C because we have no overloading. And either you write this function, or you write generic function, or you write this function with some other name and then struggling to remember this name, and so on. And I believe this is a normal vector of coevolution, normal vector of development for languages, hardware, and development tools. First, the transition from common idioms to special assembly instructions. If you have some common idiom, every sane hardware will have special instructions, special extensions to support it. Like for RISC-V, we do have ZBB instruction that introduces CLZV. CLZV instruction, which does exactly this, count leading zeros. And for x86, for ARM, for every sane architecture, you do have such instruction. And this is first vector of coevolution. Second vector of coevolution is transition from macros to generic programming. As Björn Strostrup, the creator of C++, said, any macro reveals a flow in the programming language, the program, or the programmer. And finally, the transition from compiler intrinsics to standard library function. I'm compiler developer, and I assure you, I want every compiler intrinsic to be wrapped into some standard library function because they appeared in the compiler in the first place, because they are useful. If they are useful as compiler intrinsics, they will be useful as standard library functions. Okay, let's try it in C++. Pause this video and please do rewrite find MSB in C++. 3, 2, 1. Probably you did something like this. Okay, let's try using std count L0. This is standard library function since C++20. And the first attempt to use it with signed type, find MSB at 1 is int, is occasionally ill-formed. It will lead to this compilation error. This compilation error itself provides little information about what exactly went wrong. You can pause again, please do it now, pause it, and figure out what is the error. I believe you did it. The answer is simple. Std count L0 function only exists for unsigned types. A program that cannot be translated is called an ill-formed program. This program is ill-formed for signed types because this function is not defined in standard library, in the standard library for signed types. Let's pause for a moment for this concept. A C++ program is called well-formed if it conforms to the language rules and can be translated. Otherwise, it is ill-formed and the compiler must issue a diagnostic. In some cases where the error cannot be detected during translation, like a missing function definition in another module, like we already had this situation before, the program is considered ill-formed, no diagnostics required, if and there. If and there is my favorite class of problems, like this. This is if and there, if no definition of exists. It means compiler cannot issue diagnostic on it. Like linker will do. Yes, linker will do. Oh, assembler will do. If compiler can issue diagnostic, the program is just ill-formed. If compiler cannot issue diagnostic, program is ill-formed, no diagnostics required. This is well-formed program, one of my favorite well-formed programs. This is ill-formed program. This is normative symbolic reference, like I said, on C++ standard. Okay, so what will we do now? What will we do now to rewrite this function in C++ to make it well-formed for every sane T type? Okay, let's make it unsigned. Stud make unsigned. Stud make unsigned. T is just take this type like int and return me another type like unsigned it. To fix this example, we need to ensure it works only with unsigned types. And this can be done by converting signed type to unsigned type. And now I can also not multiply to char bit or use size of. I can use stud numeric limits. Stud numeric limits colon digits. I'm using it here to get the size of the type in bits, whereas previously I used size of and char bit. I can do it because stud numeric limits digits returns the number of representable binary digits. For 32-bit signed integer, this will be 31. But now I'm sure this is unsigned, and this will be 32, and so this can be used. Okay, our code is somewhat better now. It works, it may be tested. I have some tests here on Godbolt, rather naive, but you get the idea. So, is it enough? Can you improve this further? Please pause the video now and try to figure out what else can be done. I hope you did it. Okay, first, like cosmetic improvement, some local variables may be auto. Also, if we don't want every variable to be auto because function returns int, and we don't want to make the signature depends on details of realization of implementation. So this is an int, and so this is an int to return to be sure that that there are input still results in -1. But what about user-defined types? We are in C++, and some types may be wired. We may some int-like type, like modular int, and who knows what means make unsigned for it, what means numeric limits digits for it. You have the whole bunch of yourself specializations. And we can and should apply concept. And in this course, we will have a whole lecture about concepts. To the function restricting the template to only integral types, to support user-defined types with other overloads. You overload find MSB for modular int, and now modular int is also supported. But it is not our business as a developers of these functions in the first place to um, like to support every imaginable user type. Yes, we just behave politely. We say this concept is the only we know about and no only we support, and for all other types which are not inside this concept, this function is just undefined. Go ahead, overload it yourself. Great. This syntax, by the way, student integral auto, in my view, is the only correct way to use auto for local variables. You may use it here, student integral auto digits. It's just fine for local variable. Student integral auto leading zeros, because auto itself is a little too broad. And concept auto indicates a type satisfying a specific concept. It is still obtained by type deduction, but type deduction is constrained by this concept. This is very important. And where did the template parameter go? Okay, it is hidden here, this auto. This auto means just template parameter. That is why I'm tolerant to it, because I'm not very tolerant to auto here. It is possible, but not for public APIs. And I'm really tolerable about auto here. It is just a template parameter in disguise. Okay, but we do have some problem. Little issue with unsigned char. You see, I made explicit template specialization. If you don't know this syntax, don't worry. We will have separate lecture about function templates, and we will dive deep into such template specializations. And I'm doing this just to see the assembly code. Why would I see, and I would see, slightly worse assembly for unsigned char? Let me just even show you this assembly. This is assembly for unsigned int, and for x86 now, I will often show you assembly language of different architectures, because if you know single assembly language, you know them all. And this assembly is perfect. It is just 3 instructions and then return, and one of these instructions is LZCNT, like count leading zeros, as you may guess. But this is awful. For unsigned char, it is awful, because LZCNT do not support unsigned chars. Compiler silently promotes everything to int, and then this is conditional move. This is conditional control flow, which is somewhat slower. It depends on this condition, and it is worse. How can we fix it? And we may notice that this code here is appeared only because we need to return -1 if input is 0, which is itself strange, because what is most significant bit of 0? Why do we returning -1? Why don't we throw the exception, or maybe return stood expected, or do something else? Like, this situation just cannot happen. And consider you for some reasons you sure it will not happen. And then you can optimize code in some dangerous way. Let's see it. You state if value is equal 0, this is unreachable. I call this the Grandmaster sacrifices the exchange. And in Russian language, this is a wordplay. Sacrifice exchange in Russian sounds the same as sacrifice quality. And we are definitely sacrificing quality of this code. We state, if the input is 0, the behavior of this function is undefined. And note, It's not the compiler introducing UB for you. No, we introduced it. For what? Oh, for this. You had this assembly for unsigned char, and now we have this. And this is much better. These do not have any tests for some conditions. It do not have conditional moves. If you set up the benchmark correctly, and this is benchmark, the difference will be noticeable these 3 times. You can click the link to this benchmark and admire how I set it up. It's all fair. Sleight of hand and no fraud. I merely call the MSB finding function 10,000 times in a loop and in another loop. And I never call it with 0, of course. And accordingly, here is the old inefficient code, and here 3 times better is new efficient code. But this comes with a cost. The function can be much better optimized, but now, if the precondition is violated, the compiler has the right to kill your kitten. I know in English there are nasal demons that like flies out of your nose, but I will stick to kittens. Kittens are in edge. It can do anything. Compiler, if you reached the unreachable, compiler can do anything, including something really unexpected. Really unexpected. And what exactly happened if you pass something wrong? Let me show you an example of that kitten. Okay. Now you can see this example on the screen. I believe you do. And this is our great MSB finding function. Probably we need to slightly adjust viewport because, yes, like this. This is our MSB finding function. And this is unreachable. Yes, great. And this is our code. And this is how I call it, like find MSB -1 returns, of course, 31. 31th bit, if we count bits from 0, is correct answer here. If I 8, we will see like 3. Okay, it works. And what if I call it for 0? What if I violate and this unreachable? And what if I use undefined behavior? Everything can happen, but what will happen actually is really wild. You see? This is infinite loop of 31 numbers. We have not only 31, we have 31, 31, 31, 31. But wait, we have no loops. It is wild. And we can document it better than a comment. We can document with a contract. We can state that the function behavior for input 0 is undefined. We will actually talk a bit about contracts in these lectures, and we will examine in more detail how this will look soon. And there is already a fork of Clang compiler with contracts. I would show you, but we are in a hurry to return to our dead kittens. And to explain you what's happening and what is the very soul of C++, and of course, the very soul of C++ is program behavior. And to explain you this, I shall explain you what is abstract machine of C++. This is introductory lecture, and we need to set up our introductory notions. Okay. What is the abstract machine of the C++ language? It is not a computer model. A computer model is more like the concrete machine of the Java language. The abstract machine of C++ is what all the semantic descriptions in the standard define. Let's read the standard. The semantics description in this document, this means all semantic description in this document. Define a parameterized, non-deterministic abstract machine. You see, the abstract machine is you reading the C++ code and making it in the perfect way, making no errors. When you're reading this code, you don't need to execute it. You may execute it here in your head. What will be produced out of this code? Will those calculations be here? And the correct answer is maybe, maybe not, depending on compiler optimizations. And in this course, we will always assume good level of compiler optimizations. We will assume that compiler optimizes everything for you, because if you don't use compiler optimizations, why are you using C++ in the first place? There are plenty of slower languages with much better safety. Okay, so with decent level of compiler optimizations, this will be optimized to return 0. Why? The compiler has the right to remove it because it have no side effects. I want to emphasize, one cannot say that abstract machine is defined somewhere in the C++ standard. Entire C++ standard defines the abstract machines. And the compiler does not generate code for the abstract machine. It preserves the observable behavior of the standard machine, of the abstract machine, during transformations of your code. And what is observable behavior of the abstract machine? How can I make this line survive any compiler optimization in this world? Please pause this video and try to guess. 3, 2, 1. I can add volatile here, yes? Just volatile. Volatile in G. And volatile can be read as may change unpredictably. Volatile means unknown side effects. And largely, volatile could be the only variety of side effects. By the way, it's funny that const volatile int requires an initializer. It requires initializer because it const. But what do we know about its value immediately after initialization? That is arbitrary, despite being const, so in a sense volatile overrides const. Then why have const on it? So you can change it. Yes, well, seemingly, why you want to change if it is volatile and any changes you make would be overwritten anyway? I don't know. And nobody knows, but this is perfectly legal C++. And according to this, volatile writes any write or read from volatile variable is side effect in abstract machine. And everything the translator can do is regulated by the so-called as-if rule. The compiler can do anything it wants with your program as long as the observable behavior is preserved. That is, the sequence of accesses through volatile GL-value expressions, roughly the sequence of write to volatile variables and read from them, is preserved. Also, the sequence of writing data to files is preserved, and the input and output dynamics of interactive devices, whatnot, are preserved. Okay, let's consider this neat example, which has been a bone of contention for so long. Clang and GCC still, for latest Clang and GCC, even though I've been giving this task to students for 4 years now, optimize this code differently. GCC considers both the write and the read from side effects, and Clang considers only the write to A as a side effect. And in the homework, you will be asked to look into the standard and figure out which one is right. And this is not obvious, because Okay, obvious answer is GCC, right? But we are talking about null pointers, yes? And null pointers are special, and we will have a lecture when we will talk about pointers, including null pointers, and why they are so special. And if you also submit a patch to either compiler fixing this, you will be invaluable. Yes. And every student in this room, if they will submit this patch, they will score a perfect 10. Okay. Somebody tried last year's. Nobody succeeds. Okay. But compiler not only follows SIF rule, it follows SIF rule in some extended way because compiler must be conservative. Look at this code and relate it to the SIF rule. Do you think there are volatile variables here? There are no. If they are writing to files, perhaps there is input-output dynamics on devices. Nevertheless, the compiler cannot eliminate these computations. Why? Why not return 0 according to abstract machine rules? Yes. What is here? And there is linkage. There is external linkage, meaning this function can be used elsewhere. And the compiler does not know where this value will be used, and it doesn't know if it might be written to a volatile variable somewhere, output to a file, and so on and so forth. But in general, the fact that the compiler doesn't know if it might be written to a volatile variable somewhere is sufficient. Okay, this function returns something. This something can be written to the volatile variable, that's all. If you don't know that it is not or it cannot, then you cannot optimize it away. You shall return proper result here. And the scope within which the compiler can track all connections is called a translation unit because it is unit where the process of the translation takes place. For C language, translation unit is a file. For the C++ language, we will have a separate lecture about models, translation units, and how models and translation units interoperate in the modern C++. So we must be conservative here because we don't know the entire context outside our translation unit. And let's remember this. Please note this really important concept of translation unit. And we must go deeper and discuss how conservative the compiler shall be. How conservative is the C++ language itself? One of my favorite slides, my colleague Vladislav and I recently gave a talk on this topic at the Zero Cost Conf conference in Russian, of course. Can we hoist the store out of the loop? Pause the video now and try to answer. First, can we or can't we? And if we can, will the compiler hoist it up or down? Like this arrow or this arrow? 3, 2, 1. Correct answer. Yes, we can. And we will hoist it downward. The compiler will always hoist the store downward because remember, just remember it by heart. Loads are always hoisted upward because something might depend on load result. And stores are always sunk down because they might depend on something. We are shortening the life range of dependencies. That is what we do as a compilers. But why can this be done at all? Why? The answer is yes. Because imagine if D is somehow the same pointer that is A, then it is really disruptive. You cannot haste it. You just need to apply this every iteration. And for this to happen, to make compiler be less conservative, to make it less depend on boundaries of concrete translation unit, we do have the strict aliasing rules. And the strict aliasing rules are formulated roughly as follows. A variable can alias an object of its own dynamic type, an unsigned version of its own type, char, unsigned char, stood byte, like this. That's all. An int and a double cannot alias. Int pointer and double pointer dereference them, they cannot alias. If they are, this is undefined behavior, and compiler can kill your kitten in any way it wants. And we have the dubious option F no strict aliasing, which blocks this and immediately makes everything, including performance, significantly worse. Okay, but what is this undefined behavior? What helps us to reason about such cases? And there are some details of the abstract machine. The abstract machine has three main properties. It is parameterized, non-deterministic, and not defined everywhere. Let's start with parameterization. What is n bits? Which value it is? For me, it is 32 on this exact notebook. For you, I don't know. It is an implementation defined value. Your compiler implementation must document what n bits will be in this case. Next, non-deterministic. Consider we have two arrays of 4 characters. Both are converted to pointers with this plus sign. And the pointers, are they equal or not? What is here, true or false? And this is called unspecified. This means even in the different runs of execution of the single program, the answer may differ. And both are correct. True correct and false correct. Both answers are correct, they may differ, they both correct, everything is okay. And this is not defined everywhere. This is very interesting. And this is precisely what allows undefined behavior. Undefined behavior is very important. It gives the optimizer free rein. Because yes, we did this, and we did this, and we can do this. Syntactically we can, semantically we can, but nevertheless, this function is optimized as if we didn't. Undefined behavior, no one will warn you. Why? Because undefined behavior is needed precisely to tell the compiler, I, a developer, somehow know this won't happen. Either through types, explicit annotation, language level UB, anything you want. In the translation model of the C++ programming language, undefined behavior used for this. You are telling the compiler this won't happen, to give the optimizer some freedom to optimize. Because in the statically translated language, once translation is finished, all bets are off. And to make translation in static environment, you need some freedom, and undefined behavior just gives you this freedom. And undefined behavior is dangerous. How many iterations will this loop perform? It might perform an infinite number of iterations. Why? Because the compiler sees that if ++k will overflow, and this will overflow, this array D will overflow if ++k returns 16, because maximum allowed number of element in D is 15. So it can overflow, and array overflow is undefined behavior. Therefore, it cannot happen. Undefined behavior cannot happen. You somehow tells compiler it cannot happen. Therefore, if you are doing this, you know for some reason that car never reaches 16. Maybe something inside this loop. Maybe something else. Maybe you promised to just press Ctrl+C. Yes. something. And if k is never reached 16 and compiler is sure k is never reached 16 here, compiler remove this check. Compiler remove this check, this loop is infinite loop. You told the compiler the loop is infinite. And please note the standard. However, if any execution contains an undefined operation, blah blah blah, not even with regard to operations preceding the first undefined operation. Compiler may do anything with any preceding code. Okay, and compiler is blind to B. I really like this example too, by the way, because I showed one possibility for legitimate optimizations here. GCC will do this. GCC will do infinite loop out of here, of course, because I cannot overflow. Okay. And what will Clang do? And if you click on this link, you may assure yourself Clang will remove everything. It will leave only the function label even without a return, because the compiler has the right to do anything with any code that leads to or follows from undefined behavior, including removing it along all path. And this year, there was another outburst from Linus Torvalds regarding UB-based optimizations in compilers. In the 20th LLVM version, a patch was submitted, this patch. And what does the patch do? Let me illustrate this perfect compiler optimization for you. The patch takes code like this, and LLVM 19 optimizes this code like this. Let's see what LLVM 19 does. It honestly compared with 9, jumped here, compares with 2, jumped here. It compares with everything. It compares with 0, with 2, with 9, and default case. 3 cases, 4 cases, 4 cases, 3 possible jumps. It honestly performed the division, this division, and in some cases it generates a division by 0. Adding insult to injury, in RISC-V, division by 0 is well defined and returns 1. So for architecture, for RISC-V, it isn't even undefined behavior for hardware. But here, obviously, according to this case, to case 2, here is obviously UB, right? If you go down this path, case 2, then it's UB. What does this mean from the compiler's perspective? It means it cannot happen. And what does it imply? It implies n is never 2. For some reasons outside of this function, for reasons known to you, not to compiler, n is simply never 2, and then it turns out that the compiler had the right to optimize it as if n is never 2. For example, like this, and after this modus patch, DRM in Linux broke. There was an excellent discussion. I provided link to this discussion, and I also included quote from it here. Well, what can I say? Mr. Torvalds in his usual style. But this situation made me think. It made me think about what is the best UB sanitizer in a compiler. And the best UB sanitizer in a compiler is the compiler's ability to mechanically remove any code leading to UB, including the UB itself. This is absolutely safe, and most important, it is very noticeable. Because before we will go further, let me show you some example of how GCC optimizes this code, because it is funny, and we love funny compiler optimizations. So please look at this code. This, as I said, this is how Clang did it. And Clang just removed comparison with 2. You see, there is comparison with 9, comparison with 1, no comparison with 2, because 2 can never happen. And division by 0 can never happen either. Okay, and this what GCC did. And GCC just used table, and this is the table. For 0 it is 7, for 2 it is 0, for 9 it is 4, and for other values it is 1. And what is funny? And funny here, funny enough, I believe, is what will happen if I put here like 16. What do you think? And for 16, oh, for 16 we do have a 16 value table. And where did it stop? Please do yourself some investigation and where will it stop. And like it will definitely stop if I will write 1 million, yes. Or not. And this is funny investigation. You will get some number like 25. It is not even the power of 2, yes. And then please answer, looking into the GCC sources, why 25? It is interesting. Okay, and I want to propose anybody in this room a golden opportunity to score a 10 for this course. We will study C++. We'll study C++ in depth. And fortunately, most industrial compilers are written in C++. GCC, Clang, name your compiler. Take any UB. Vlad Belov proposes this UB. Like, this function takes const pointer, and of course, it is UB if it changes P2. And it can change P2 with const cast, okay? But this is UB. So P1 is always equal P2. So this can be dropped and this can be dropped. And all these lines just return 14. Okay? And now no compiler optimized it this way. No compiler dropped this code. So task is integrate into any industrial compiler, or better yet, into both, any patch that removes code leading to UB. Simply remove it in all branches. It's simple. In this audience, there are enough students with a history of commits to LLVM, including upstream. Please, go ahead. Use this opportunity. And let me scare you now. Suppose I understood the danger of UB. I am decent C++ programming. UB is dangerous. Okay, what will I do? I want to protect myself from UB in C++. And now I written these checks. I protected myself, am I not? If offset is greater than 0, and the same time base is greater than base plus offset, return 42. Otherwise, the reference, of course, we will never overflow integer, or we not. And if I will look into generated assembly, compiler just drop this code. Drop this code because UB cannot happen. Integer overflow just cannot be here. That is why those checks are in vain. You get the idea, right? Compiler will remove it, it did remove it, and it will always remove it. And for a lot of C++ programmers, there are common story. We will very often encounter the compiler removing your code. The compiler removes your code for two reasons. And we have both reasons in this lecture. The first reason the compiler removes your code is the as-if rule. If your code does not affect the side effects in the program, the compiler will remove it for sure. The second reason is undefined behavior. If your code on any path leads to undefined behavior or passes through the undefined behavior, the compiler has the right to remove it. And this somehow irritates many people. Here on the slide, an example is given. Calling the function with the argument true returns 42. Why do you think? Of course, reading the uninitialized variable simply cannot happen. Therefore, variable c is always false. It is your telling the compiler C is always false here. And even if you pass true there, it's always false. Somehow this bothers many people. Agree. Somehow I don't even understand why it bothers so many people. Perhaps it's the insufficient boldness of these people. I believe I'm sufficiently bold. Or maybe their insufficient readiness to write in our beloved language, to optimize by inserting stud undefined, all that sort of thing. Therefore, in C++23, a new type of behavior was introduced, and in C++26 it received its first concrete content. This is not UB, this is EB, erroneous behavior. What is erroneous behavior? Erroneous behavior is roughly like this. Starting from C++26, for your variable to truly be non-deterministic, you must apply the indeterminate attribute. This has already been accepted into the standard, and if you apply nothing, then A contains some garbage. Any garbage from the stack, but the operation of reading it is not an undefined behavior. The operation of reading it is erroneous behavior. Garbage in, garbage out. A contains some garbage. Now C here contains some garbage. But the compiler is not allowed to remove this line, nor all paths leading to it. But here it is allowed because this is still UB. And of course, because it allowed to remove this line, it allowed to remove this line as well, but not for the reasons of this line. Yes. Erroneous behavior is, for example, adding some value to A. In general, reading A is erroneous behavior. And note that erroneous behavior is well-defined behavior. Implementation are recommended to diagnose. When you do something incorrect, the compiler allows you to do it, but doesn't cause catastrophic consequences, like in UB cases. In C++26, besides erroneous behavior, erroneous values appeared. This is C. D is equal to C. This is not an erroneous behavior. D now contains erroneous value. And assert C equals D holds because both integral promotions have erroneous behavior. They return something erroneous, something not defined, but they return the same undefined things for all function calling it. I really like how this is formulated in the standard regarding translation semantics. When storage for an object is allocated, we will soon talk about what an object is and what storage for them is. The bytes obtained upon allocation have the following initial value. If object blah 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 marked with indeterminate, the bytes have indeterminate values. Otherwise, the bytes have erroneous values, where each value is determined implementation independently of the state of the program. Pay attention. Independently of the program state. You cannot control what values formed there. The standard only guarantees this. Okay, and now homework assignment. The first homework assignment will be easy, only 3 tasks, each worth 1 point. First task, read the standard, send the answer who is right. If you commit a patch to some industrial compiler, you will get much more for it. Next, dereferencing a null pointer. Who thinks that dereferencing a null pointer is UB? Looking at this slide, no one thinks so anymore. Find another elegant example. And note I dereferenced the null pointer, and this is not even an exception. An exception would occur if I had virtual functions in the dynamic type. If A is a null pointer but a pointer to a derived class, and I reference it inside type ID and the base class had virtual function, then it will be some stood bad type ID exception. In this case, it simply returns some name and you will see it on the screen. Generally, determining whether dereferencing a null pointer is UB or not is very non-trivial. So please go ahead, write some interesting examples of how to dereferencing a null pointer properly. And third task. You remember this code? I tried a couple slides ago to write protection for it, but I didn't not succeed. Write it so that it is protected against the maximum number of undefined behavior cases. Standard is C++23. All assignments are C++23 except those using reflection. There will be a separate lecture in this course on reflection. And assignment for that, of course, in C++26. Fortunately, there is a Clang fork with implemented reflection. So we will have no problems in making this assignment. There are many possible UBs, not only integer overflow. Protect this function as good as possible. If you protect it in a way I like, you will get 1 point. Okay, and now some literature. First, the language standard. This link will always be here. You must read the standard and understand it. Of course, this course is based on the C++23 standard. Next, Out of Respect. Björn Strostrup, the creator of the language, a good book, but probably if you are in this course, it is already useless for you. Pay attention to this talk by Chandler Karuch. It is essential viewing. Chandler is a brilliant speaker. Unfortunately, he moved to Carbon language, which he himself conceived. Next, the motivating talk of Piotr Padlevsky, Undefined Behavior is Awesome. As a compiler developer, I agree, Undefined Behavior is awesome. Piotr gave this talk in 2017 when he was still young. A very well delivered talk, highly recommended. And of course, have Satur, this here, CPP on C. This video is very good. Okay. Now let's talk how this course will look overall. In the first part, we will talk about generic programming. In the next lecture, we will generalize strings and see where it leads us. Perhaps we will invent class templates, template functions, so on. And in the first semester, we will sequentially cover everything that can be done at compile time. Function templates, overload resolution rules, class templates, instantiation rules, overload resolution rules. Okay, I already said this. Concepts, context-dependent computations, ranges, reflection, and everything else related to translation. Modules will be definitely covered and quite early. Those who watched my talk on modules at C++ Russia probably won't learn anything radically new, but I love this topic very much. In the second semester, we will talk about runtime mechanisms that currently cannot or almost cannot be done at compile time. Dynamic polymorphism, allocators, multithreading, canonics, coroutines. Although I think multithreading will also be soon doable at compile time as coroutines are. Next time, we will continue our immersion into generic programming and talk about genericalizes and talk about